Hello and welcome back to Calculus 3. This is section 16.6 on center of mass. It is a very short section. We are learning formulas, and then you will just use whatever appropriate integration needs to be used regarding the shape you have to solve the problem. We are talking about three different types. There are objects that are very long, so we can just regard those objects as a pure length, in which case we will be regarded as a one-dimensional object. And it will have as a center of mass some value x0 or x bar. Maybe it's better to call it x bar. Let's just call it x bar, without worrying about anything else. Then you might have some kind of a shape that is a two-dimensional shape. You know, it could be a flat plane, could be, you know, a long piece of, large piece of plywood or a drywall or this whiteboard, this detachable Surface keyboard, right, for Microsoft Surface. So whatever would be like that, leaf on a tree, right? So whatever you have that is extremely thin for its size, these are all 3D objects, but they can be regarded as a 2D object. So now you're going to have a point somewhere, right, where you will be able to balance it, and that point would be x bar comma y bar, because that's the only thing that counts. And then you are going to have some three-dimensional shape. You can think of a car, or you can think of a plane or whatever, and I'm going to represent that as a box, let's say, and that will have somewhere within that object will have x bar, y bar, z bar, center of mass, meaning that the object is perfectly balanced at that point. Now, why is it important to know this point? Because when you are dealing with physical systems, and this is very important for you mechanical engineers, when you're dealing with physical systems, you will draw all of the forces as acting at that center of mass. This is why in physics they replace an elephant with a point. You don't get to replace an elephant with a point. It's a 1-ton animal, right? You don't get to swipe that under the rug. But the trick is that that elephant is a three-dimensional creature, object, that does have a center of mass somewhere. You can tip an elephant. Well, maybe you can't, I can. So you get to replace the entire elephant with a single point, and then you just apply all of the forces there. You will go to the center of mass of the elephant, and you will draw an arrow down and say the weight of the elephant. And then you will draw the arrow up and say normal force for the elephant. And if you are pushing the elephant for one of the sides, you are going to put the arrow going into the point and call it force F, which is equal to m times a, mass times acceleration, right, to push the elephant. The elephant could be going up the incline, down the incline, sliding, and right, on roller skates or whatever. You can come up with fun stuff, right, for physics problem, but the whole elephant is replaced by one point because of this section in math, right? So the point of the center of mass can be one-dimensional, two-dimensional, or three-dimensional. Now, when we start talking about these things, we first talk about the mass integral, because the integral for the mass depends on the density of the object. Denser objects are more massive than those that are less dense. Clearly, they have more particles, more interactions, and more everything, so they are heavier. See, if you are to, you can go around and joke with people what is heavier, a pound of feathers or a pound of gold, right? And then those that are not thinking will go for the gold, obviously, because feathers are very light. But then you said 1 pound of feathers, 1 pound of gold, so it's the same, right? But if I am to occupy the same amount of volume with feathers and gold, gold would be much heavier than feathers, right? if I say you come up with a box, right, and you put in feathers, and then you have a same box, and you put the gold in it, well, clearly the box of gold will be way heavier than a box of feathers. So I like to describe mass as quantification of physical existence, right? There are many definitions, and physicists are still working with mass, but when I talk about mass, I like to say, does it exist in a physical realm? Can I touch it? Can I flick it? Can I lift it, right? And then you have those that do not exist in a physical realm, like love. Well, there's no mass to love, right? So mass would be quantification of physical existence. We're going to have an integral for that. And depending on the dimension you're in, it's always going to be some kind of integral of a density function rho. So I'm just going to leave it like this. You know what? Let's go with the one dimension before. So 1D case. How about that? So mass in one dimension is given as integral a to b, because it's just a long rod or a baseball bat or something. So integral a to b of the density function and then dx. So rho of x is the density function. It could be uniform density. Let's say the entire rod is made out of the same metal, pure metal. Rod of gold, right? Just gold. That's it. Well, in that case, the density would be uniform, and the mass of the object would be uniform, and you have to have the center of mass to be exactly in the center of that rod. But then if there are impurities added, if there are mixtures of different materials, two materials stuck together, then the density is not uniform, which means that the center of mass is not going to be in the middle of the rod. Because I can stitch together a little bit of copper and a little bit of lead. And if they are the same length, well, copper on one side is much lighter than the lead on the other. So the density has to be on the side where the lead is. Right? Still 0 to L. But the distance over here has to be like that. So rho of x not uniform. Have to be careful about those things. So now, how do we find the x bar? Well, what you calculate first is the moment around the point where the center of mass is. And that is going to be given as x rho x dx from AB. So you have this equation to calculate mass, this equation to calculate the moment, and then x bar is the moment divided by mass. And that is your x coordinate where you have, right? So that's one dimensional case. So clearly just Calc 1 integrals, nothing special there. 2D is interesting because 2D we get to use double integrals. So mass is going to be given as a double integral over region R of density function xy dA. Now this is the general integral, guys. This is the general integral. Now you are going to have the moment around y as a double integral x rho xy dA, and moment about x, again, double integral over r, y, rho xy dA. And these formulas here will give rise to x bar equals my over m and y bar equals mx over m. These are the formulas that you use to calculate center of mass. Now I need to explain this stuff so it makes sense. Behold a two-dimensional object, right? Which is non-uniform in rho because this part has a lot more plastic than this part here. So if I am to just draw diagonals and find the center, it's not going to be that because it will flip that way because this part of the keyboard is heavier than this part here. It's a very simple, common sense thing. So the center of mass will not be in the center, it will be more this way, somewhere to accommodate extra plastic and extra stuff. Now, why is this all mixed like this? The moment of y and you use x and so on. Now look at this, guys. If I say that this is the x-axis, the object wobbles in y direction, right? And if it is a y direction, it wobbles in x direction, right? So for y direction, wobbles in x. For x direction, wobbles in y, which is why they are like that. The moment simply means it turns around that point. Anytime you have here, for one dimension, you see that? It rotates around the point first and then falls. That's the physics. So look, as soon as I let go, it will rotate first and then fall. See that? So that's what this stuff is, right here. Now, for this object, if I put the x-axis, it will rotate in y direction first and then fall. So that's why we have moment around y-axis, moment around x-axis, but then it's x direction, it's y direction, right? And you get your x bar and y bar because they go x with the x and y with y, just like you had for one dimension. Now, these are general integrals. It depends on the shape, what integration you are going to use. Your shape could be a rectangle, right? You use xy. Your shape could be a circle. You use polar integrals, double integrals, right? Could be a flower, again, polar integrals. Annulus, polar. Cardoid, polar integral. Rectangle, rectangular integrals. Triangle, rectangular. Trapezoid, rectangular. So there are a whole bunch of shapes that you can have as a two-dimensional object. Which integrals you are using in the formulas depends on what shape you have. So these are the formulas that tell you what to do. The integral within them, right? You will be setting up either dx dy or dr d theta. Does that make sense? And for 3D, we have our mass integral as a triple integral over the region S, shape S, of the density function xyz dv. We have now moments on xy is going to be the triple integral region S of x rho xy z dv. Moment on xz, triple integral y rho xyz. And finally, moment on xy, triple integral over the region S Z. And when you compute these four, you will be able to calculate x bar, myz divided by m, y bar, mxz divided by m, and z bar, mxy divided by m, so you're just dividing numbers. So let's go to homework and solve one of the problems they have to figure out center of mass. Please, some common sense, please. The center of mass should be within the object. I won't be balancing this one with the point that it's here, because it doesn't rest on the point at all. Right? 0 to 10 and 0 to 10, please don't give me a negative value, because it has to be somewhere from 0 to 10, 0 to 10. It has to be within the bounds of the object. Let's see what we have. It doesn't matter, pick anything. The solid bounded by the paraboloid z equals x squared plus y squared, and the plane z equals 25. Okay. I'm going to draw this because that's the way when it's, and they want us to do what? Find the center of mass of the following solid with a constant density 1. Woohoo! Rho equals 1. Well, that simplifies things greatly. I have a paraboloid. X, y, z. The top over here is at 25. Z equals 25 is the plane that cuts it on top. So we have this paraboloid with the plane on top. So now we would like to find the center of mass. Well, if we use symmetry here, being that it's uniform density, I hope you immediately see that the center of mass must be on z-axis, right? Do we agree? Because it's radially symmetric. So it must be on a z-axis somewhere. And the only reason why it's on the z-axis is because everything else is radially symmetric, right? So, and the density everywhere is 1. So it's uniform density, and we don't have to worry about any of those calculations. So the only one that we are worrying about is actually the z bar. We know that x bar equals y bar equals 0 because it has to be on x. Has to be on z-axis in this particular problem. Because rho equals 1 plus shape. So you know what I mean on there. Okay, so how do I find z bar? I find z bar when I take the moment xy and divide by the mass m. Moment xy was the triple integral over region S of z times rho of xyz times dv. Great. So now I get to set this up. mxy is equal to the triple integral. Now, the shape of the problem is going into the limits. And what I have is a z-axis is going... Oh, I get to decide which coordinates I'm going to use. I have rectangular, cylindrical, and spherical. Which coordinates do I get to use easily here? Looking at the shape. Which one? Spherical. It's not a sphere, and I have a flat plane, so I'm trying to avoid spherical. Cylindrical. It's a round object which does not contain ball, right? So let's use cylindrical. So now for cylindrical coordinates z, z, rho is 1, dz, r, dr, d theta, right, using cylindrical coordinates. The top is 25, z equals 25. The bottom is r squared, because x squared plus y squared equal r squared in a conversion for polar coordinates, or cylindrical polar. Radius r, 0 to 5. The fattest is at the top, when it's 25, x squared plus y squared equals 25, so 5 in radius up there, and 0 in radius on the bottom. And we want 0 to 2 pi. We want the whole shape. So mxy is equal to, and now we just need to integrate this, 0, 0, 2 pi, and the 5. Integral of z is z squared over 2 calculated from r squared to 25. And I still have r dr d theta. That's integral, double integral, 0, 2 pi, and the 5. I have 25 squared is 625 over 2, minus r to the 4 over 2. All of that times r, dr, d theta. So now we distribute. You can kick 1/2 outside. And we have 625r minus r to the 5, dr, d theta. This is 1/2 integral 0 to 2 pi. When I integrate, I get 625r squared over 2 minus r to the 6 over 6 from 0 to 5, d theta. You can kick another 1/2 outside, so now it's a 1/4 there. Integral 0 to 2 pi. And now, plugging in 0, it's going to wipe it all off, so just 5. 625 is 5 to the 4th. And now you have another 5 squared. So that's altogether 5 to the 6. Minus 5 to the 6 over 6. So you don't need a calculator for these things. It's simple calculation. So 1 over 4, integral 0 to 2 pi. I have 5 to the 6 minus 5 to the 6 over 6. Right? So if this is 6 over 6 over here, that's going to be 5 to the 7 over 6. When you subtract d theta, that's another constant, so 5 to the 7 divided by 24 times 2 pi, so this is 12, and that's a pi. So I calculated that mxy is 5 to the 7 pi over 12. Now I need to find the mass. And the mass is the same triple integral with same limits, same everything. You're integrating 1. dz, r, dr, d theta. And then you just divide this with whatever you get, and you're done. 0 to 2 pi, 0 to 5. It's 25 on top over here. And r squared on the bottom. Integral 0, 0. 2 pi and 5, z, that's going to be 25 minus r squared times r dr d theta, double integral 0, 0, 2 pi and 5, that's 25r minus r cubed, dr d theta. Now integrate r, 25 r squared over 2 minus r to the 4 over 4 from 0 to 5 d theta 0 to 2 pi, and again 525, so this is going to be 5 to the 4 over 2 minus 5 to the 4 over 4. I can kick out a half d theta 1/2 integral 0 to 2 pi, and I have, again, if I put a 2 and a 2, it's going to be times 2 times 2. It's going to be 5 to the 4 over 2. D theta. So that's 1/4, well, 5 over 4 over 4 times 2 pi is going to be 5 to the 4 pi over 2. So z bar is moment xy divided by the mass. That's 5 to the 7 pi over, I believe we had 6, no, we had 12, over 12, divided by 5 to the 4 pi over 2. Whole bunch of stuff cancels. Pi is canceled. 5 to the 7 and 5 to the 4, you get 5 to the 3. And this cancels, you get a 6. So you have 5 to the 3 divided by 6. That's 125 divided by 6. Z bar is approximately equal to 6 into 12 goes twice, 6 into 5 goes 0 times, 6 into 50 goes 8 times. That's 26 and 20 goes 3 times, so it should be like this, right, forever. 20.83333, I hope. That's good enough. Does this make sense for center of mass to be at 0, 0, 20.83? Well, yeah. This object looks like this, right? So this object looks like that, right? And this is where the 0 is, and this is where the 25 is. And let's say this is where 20.8 is. Do you see that this part is much fatter than the bottom part? Right? So the mass that it's above this point and the mass that are below this point are the same. That's the trick, right? You can't, if you put a triangle, mass-wise, half cannot be here because there will be that's a half of height, but it's not a half of mass, because if you compare this much with all of this, there's more here because it's fatter, right? So when you are done with these problems, you can actually use common sense to see if the answer makes sense. Obviously, if we got a number that it's not between 0 and 25, you immediately know it's garbage answer, right? Because the center of mass better be within the object. You can't balance the object outside of the object. And also, I want this point to be as closer to the top, because that's where the object is fatter. It's bigger right there than the bottom. Bottom is skinnier. So more of the weight and more of the mass, right? More of the mass. Weight is mass times gravity, so it's force. The mass, right? When you buy 1 kilogram bananas, it's 1 kilogram here, and it's 1 kilogram on the moon, right? It's the same. Mass does not depend on gravity. The weight depends on gravity, so your your weight is less on the moon because the gravity of the moon is much smaller than the gravity of the Earth, so you're multiplying by much smaller number, so your weight is going to be much smaller on the moon. Same for the Mars, which is the issue. If we are to live on Mars, yeah, we can deal with the poisonous soil, we can deal with the poisonous atmosphere and all of that, right? You just build terraforming. People live in 6 months in space in ISS, right? The International Space Station. So yeah, we can survive on Mars. The issue is the lower gravity. So if you have a generation of people that are born on Mars, they are not going to have the same strength and bone structure as we have over here, because we have to fight higher gravity. So technically, if anyone from Mars after generations come here and just flick someone and kill them, right? Because you will shatter the whole person, because they will not have the same bone density and everything, because the gravity is lower. And now you going to the Mars, you'll be able to jump higher and go to the moon, you can just bounce one face down effortlessly, because the gravity is not as you're not used to that low gravity. Anyway, so talking about the center of mass, we use the triple integral here, and we use cylindrical coordinates because they are appropriate for the shape we had. Your shape could be a sphere, use the spherical coordinates. Could be something boxy, use rectangular coordinates, right, for triple. So depending on the shape, you will use whatever coordinates belong to that to that shape to calculate. The formulas which I gave over here are general formulas where I put dv, and that dv could be rectangular, the z, dy, dx, could be spherical, which would be rho squared sine phi d rho d phi d theta, or could be cylindrical, zr dr d theta. So that depends on the shape. And these puppies over here, x, y, z, you have to convert them to the appropriate system. So you know that if you're using cylindrical coordinates, instead of writing x, you will write r cosine theta. Instead of writing y, you will write r sine theta. And z stays z. We had that in our example. Z is z for cylindrical coordinates. And then we also had those conversion formulas for cylindrical coordinates, right, in a previous lecture. Let's jump spherical integrals real quick. And if you go here in blue, there they are, right? If you are using triple spherical integral, then that x, y, and z that appear in your equation, x, y, and z have to be replaced by these guys and then integrated through the system. And also, if you have a row that depends on x, y, z, then all of those as well have to be replaced by this. And you just have a huge mess that will take, very long time to untangle with algebra, and then good luck with integration. Now, obviously, for exams, those are, pushed down to a minimum, so you don't have to sit 40 minutes per problem. But when you're engineering real stuff, you hope you're designing a plane that's going to stay in flight, right? Not something that has a variable center of mass, right? So you have to be able to do these calculations if you want to be the real engineer. If you don't want to be a real engineer, there's plenty of spots in sales. So don't worry about that. So that's it. Please remember for these center of mass guys, for center of mass calculation, we are going to have all of these different integrals, and then you can use whatever appropriate coordinate system is for that section so that you can deal with it. Bye.